So this is lecture 16, and today is May 7, 2021. Okay. So we were talking about harmonically excited systems, and I want to simply summarize everything today, and we'll move forward with the next topic. Before I do that, there's one little um, topic we didn't cover. I usually go over that in full details, mathematically derive that, and so on, but I don't see a need for that. And the only reason I'm going to cover that because in the lab, you're going to encounter that in your model analysis experiment. So let me just go over that briefly, and then we summarize where we are and where we are going. So what I'm going to cover today is called bandwidth method, which is also called half power method for damping evaluation. Okay. As I said, I'm not going to go through the details of it, just introduce that to you as a kind of a rule of thumb. So when for damping evaluation of the damping coefficient, you remember we first introduced the method of logarithmic uh, decrement, which was based on the time response of a, a damped system, okay, under harmonic excitation or free vibration, doesn't matter, okay? The second approach was Q method. We call that Q method, which was what? We said that if you plot the frequency response function, okay, for a harmonically excited damped system, you get something like this. Or in the lab, of course, you do that in the model analysis, you plot the frequency response function would be something like this. If you have you already done the model analysis experiment yet? You will do that. But anyway, in that case, you consider the first mode and you say, okay, if I want to evaluate damping, one approach was what? You measure this peak value, which we call that Q, and we show that Q is roughly 1/2 zeta. But in reality, it is not easy to find them. This is kind of messy, noises involved, and so on. So it's not easy to have a reasonably accurate measure of where this peak is. You get a messy response like this, okay, frequency response. So in practice, we kind of approximately find this Q, and then what we do this. Okay, this is the frequency response function. You consider, if you approximately find that Q, okay, you consider a value of Q over the square root of 2. You draw a line parallel to the R axis or the frequency axis. This will intersect with the frequency response function at 2 points. Let's say if this is omega 1, this is omega 2. You can demonstrate that zeta can be evaluated from this relationship, okay, which we call that half power method. As I said, in the past, I have gone over this topic in details, why we call it half power, and so on. But the end result, which is all you need, frankly, for evaluation of damping, is that all those formulations result in this relationship that you can use for evaluating the damping. So this is the third approach for the evaluation of damping. Okay. So with that said, we are going to move on. Let me simply summarize what we have covered in harmonically excited systems, and then we'll start a new topic. So let's present a summary of all topics we discussed in harmonically excited systems, which of course we're talking about damped systems. Okay. We said that if you have a system under the action of a harmonic load, whether it's sine or cosine, maximum value of the response can always be found from this, right? Where h is what? Is this function. And of course, the response itself was f0 over k, h times sine omega t minus theta, where theta was the arc tangent of 2 zeta r over 1 minus r squared. Okay. Then we discussed a special type of harmonic excitation that results from a rotating unbalance. So when you have a rotating unbalance, the forcing function, the amplitude of this forcing function would be simply m sub e omega squared, where this is the location of the unbalanced mass from the center of rotation. This is the unbalanced mass, and this is the frequency of the rotation. And obviously, of course, h would still be that h would still be that 1 over 1 minus r squared plus 4 zeta r. This, so if you want to find maximum displacement, you can still write f0 over k times h, but f0, of course, in this case is that. And then we rewrote that to simplify that. We didn't like this form. We ended up with something like this. Instead of, that, we, ended up with something like 1 over m times r squared divided by 1 minus r squared plus 4 zeta squared r squared, which we call that also pseudo, you can call that pseudo frequency response function. Okay. Anyway, we also discussed input uh, time dependent displacement instead of having a direct forcing function. So we covered that topic. And then we discussed the basic concept of vibration isolation that um, is really measured by this quantity. We call that transmissibility ratio, which was this uh, function, okay? 1 minus r squared plus for zeta squared. So transmissibility ratio was the maximum uh, input to the, no, I'm sorry, the maximum forces input to the system or experienced by the system over the maximum input force, or same thing for the displacement. So we also have now discussed evaluation of damping into two different forms, either this or, in other words, zeta is 1 over 2 q, or zeta is omega 2 minus omega 1 divided by omega 2 plus omega 1. So this is basically, in a nutshell, a summary of what we discussed in harmonically excited uh, systems. So with that said, we also, obviously, we also discussed various important uh, uh, curves or plots that we encounter in force harmonic excitation, and that was uh, the frequency response function. For the first case, when you have direct sinusoidal function, you have a frequency response function that look like this. The shift of the peak value to the left of r equal to 1. And if zeta is greater than 0.71, this falls below this line. If you have a uh, unbalanced rotation due to unbalance, this is the frequency response function. With, you will see that the shift of the peak is to the right of r equal to 1. And of course, maximum response, well, I mean, the response when r goes to infinity will never reach zero, but it reaches at the maximum, in this case, reaches the static displacement. Then we also um, plotted the transmissibility ratio to have a qualitative understanding of what happens uh, in terms of the effect of either the time or displacement input. And we plotted that function, and the function looks very similar almost to the undamped, uh, I'm sorry, damped system under harmonic load, except that all these curves pass through a single point, which is at r is equal to square root of 2. And as we said, what this curve helped us was to understand what range of values for r is best for reducing the effect of external excitation. So if the frequency of the excitation is greater than square root 2 of the natural frequency, that is the best range, because the maximum uh, value of the uh, force that the system experiences is always less than the corresponding maximum input force, or same thing for the displacement. Um, and then, of course, this led us to the concept of vibration isolation, that how what how we can design a system to be best in isolating the effect of the excitation, and that was the frequency should be much less than natural uh, of the frequency of the excitation, meaning the system should be soft as much as possible, unless that it is not too soft, that the static displacement is not too much. So this is, as I said, very basic summary of what we have covered so far. And with that said, we are going to conclude now the harmonic excitation of damped system and start the new topic. And what is a new topic? We've been talking about forced vibration, right? And forced vibration was categorized into broadly into undamped and damped case, right? But also we said that depending on the type of forcing function, you categorize the response or the vibratory response of the system. And the first type of forcing functions that we covered were harmonic excitation, which we spent almost 2 weeks on that. The second type of forcing functions that we are now going to consider are periodic excitations. Periodic excitation are in a way similar to harmonic excitation in a way that they are repetitive forces, but they're not repeating themselves in a harmonic sense. For instance, if you have a cam drive in a mechanical system, is a good example. It may look like this, the forcing function, that at every period you generate a force that we call that is sawtooth behavior. The forcing function looks like this. Okay, it is repetitive in time. After every period, it repeats itself, but is not harmonic. Or you may have a function like this, which again repeats itself after each period. This is one period, right? But it is not harmonic. You may have, a variety of shapes that may occur, okay, that are not harmonic, but they're periodic. So how do we deal with forces that are of this nature? If you go back to your calculus, you remember the famous Fourier uh, series. What did Mr. Fourier uh, uh, teach us? He demonstrated that if you have a periodic function, that periodic function can be approximated in form of an infinite series. And this infinite series looks like this. You can approximate that in this form. A1 cosine of omega t plus A2 cosine of 2 omega t plus an cosine of n omega t plus b1 sine omega t plus b2 sine 2 omega t plus bn sine n omega t. Okay? Or in series form, you can simply write that as a naught plus sum of this infinite series a n cosine of n omega t plus bn sine n omega t, where in this series, or in other words, in order to set up an approximate form for these periodic functions, all you need to do first, define the mathematical form or write the mathematical expression for this function, as long as the values are given, and then evaluate these quantities. A naught can be proven that it is derived by evaluating this integral, okay? A n is the outcome of this integral, cosine of n omega t, and b sub n is the outcome of this integral. So all you need to do is evaluate, set up the function as a step one, and then evaluate these coefficients or these terms, substitute that in this series expansion, and you have an approximate form of the original function, except that the beauty of this form is that it is the sum of several harmonic functions. And why is that important? Because you remember, as we mentioned last time, that from the concept of superposition, you remember that from strength of material, right? If your material, if you're yeah, you're dealing with only the linear part of stress strain diagram. In other words, the forcing is not heavy enough that you have not reached a yield point, so these materials behave linearly, or you're within this range, or when this displacement is small, very, very small, which is what we are studying in this course, mechanical vibrations, then the effect of several forces acting on a system is the sum of the effects of each individual one. Meaning that if you have, let's say, cantilever beam subjected to, let's say, three forces, and you want to find the displacement at the tip of this beam, what do? You first find the displacement of this beam under the action of this force, okay? Find the displacement under the action of this force, find the displacement under the action of this force, okay? And if you add these up, okay, that will give you the total displacement under the action of all of these combined. That concept is applicable to vibratory system as well. That means if you have, for instance, a sum of several harmonic excitations, let's say something like this, okay? So if you have three uh, harmonic forces of different frequencies, different amplitude are acting on the system, how do you find the response of this system under the action of each of these? You know that for this one, let's say you want to find the maximum displacement. The maximum displacement would be maximum displacement due to and this, and add it up. So what is the maximum displacement on this one? Is A's F0, which is A, over K times H, right? Where H is what? That 1 minus R squared plus 4 zeta squared R squared, where R is correspond to this frequency, right? You do the same, so I called it H1. So this would be B over K times H2 plus C over K times H3. So that's the beauty of this Fourier series expansion, because you have reduced the problem into an infinite sum of harmonic forces. So for each harmonic force, as you see, you can simply find, say, the maximum response or the reason or the response itself and add them up. We'll do that in a minute by doing an example. But before that, let me just refresh your memory as far as how you do this Fourier series expansion. So I'm just going to demonstrate that through a simple example, a problem. Let's say you have a function that looks like this, and you want to replace that with its approximate value, which is the series, Fourier series expansion of this function. So this function has a period, and let's say the magnitude of the function uh, oscillates between, changes between 1 and -1, okay? So as I said, the first step, step one, is you need to set up an expression for this function. Okay. So what is this? This is a discontinuous function that its value is 1 when t is greater than 0 and is less than t over 2. You do this, you set up this function for the first period of this periodic function. So you can see that in the first period, what is this function? Is this, right? It is 1 when um, between 0 and half period, and it is -1 when t greater than half period, less than the 1 period. So that is the mathematical expression for this function during its first period. Then as the second step, what you need to do is to evaluate A naught, AN, and BN. So let's do that. And what is A naught, AN, and BN? Are these functions, okay? So, or integrals, you need to evaluate them. So let's do that for this example. So A naught is what? Is 1 over t integral from 0 to t of f of t dt. So we'll substitute for f of t. F of t is discontinuous, is changing. So the integral should be divided to 2 integral from 0 to t over half plus t over half to t. In this domain, function is 1 dt. Here it is -1 dt. That's it. Okay. So if you perform these integrations, you can easily see that the outcome of this would be simply t over 2, and the outcome of this would be simply t minus t half, okay? And these two add up to 0, so this would be 0. Therefore, a naught for this function will be 0. So let's do an. An is 2 over t, integral from 0 to t of f of t cosine of n omega t dt. So again, the integral would be um, separated into two parts from 0 to t half, where function is 1. So this is cosine of n omega t dt, plus integral from 2 t half to t, where the function is -1, so that I take the negative out, cosine n omega t dt. Okay, but what is the integral of cosine n omega t? The integral of that is 1 over n omega sine n omega t. That is the integral of that, which is the same here. Okay, so substitute for those, perform the integration, you get 2 over t, okay, 1 over n omega sine n omega t, okay, evaluated from 0 to t over 2 plus 1 over n omega sine n omega t, evaluated from t half to t, okay? Remember, omega here, omega is what? The frequency, so it's related to the period. So we just substitute for that and then put the value of t. If you do that, you end up with this, 2 over t times 1 over n omega sine of 2 pi t over t. When you substitute for omega here, perform that, same thing here, this is what you end up with. So basically you end up with sine of 2 pi, which is 0. So this is also 0. So A naught came out to be also 0. Let's do B sub n, which is 2 over t of, again, similar integral, 0 to t, half of this time ft times sine n omega t dt plus integral t over half t, -1, so negative comes out, sine n omega t dt. So we need to perform this integration. Integral of sine n omega t is -1 over n omega cosine n omega t. So that's the integral for that function. So again, if you substitute that, I don't go through the details. If you substitute that, substitute for omega is equal to 2 pi over t, evaluate this whole thing, you see that Bn comes out to be this value. If n values are odd, 1, 3, 5, and so on, Bn would be simply 4 over n pi. And if n values are even, it would be 0. So Bn has values only for the case that n are odd, okay? So this is Bn. Therefore, the function or the series expansion, Fourier series expansion of the function can be written as A naught, which is 0, plus sum of n going from 1 to infinity of an times cosine, which an is 0, so that term doesn't exist, plus bn, and bn is 4 over n pi of sine n omega t. I write it in terms of omega, I write it in terms of the period, so it would be 2n pi over t, okay, where of course n would be 1, 3, 5, and so on. So this is the approximation for this function, okay? So physically, what does that mean, or mathematically, what does that mean? If you plot this function, let's do that. If you plot that, so this was the original function we are trying to approximate using this series, Fourier series expansion, okay? So this is the, now let's plot this. If you consider just n is equal to 3, okay? So in other words, you have only 3 terms here, okay? You see that if you plot that function, it looks like something like this. It will look something like this. And as n increases, you'll see that it kind of smoothes out and approaches this. Versus if you consider, let's say, roughly n is equal to 20, and you plot that, you see that you end up with something almost like this. Okay. So the function, the series representation of that function approaches the original function. So you, by increasing number of n's, you can approximately reach the same shape, except that the benefit of this form is a sum of several harmonic functions. Okay. So with that said, let me summarize now where we are and what we are doing here. So what we said was, if you have a damped system under the action of a, a periodic function, this periodic function in general can be written in this mathematical series summation, right? An cosine n omega t plus bn sine n omega t, where a naught was 1 over t. This integral evaluated for the first period of that function. A n is 2 over t evaluated during that period, cosine of n omega t, and bn is 2 over t, 0 to t of f of t sine n omega t dt. Okay, so the periodic excitation reduces down to this equation of motion. Now, we remember from harmonic excitation that if you had just a single harmonic force like this, right? Response was what? Was F0 over K times H sine of omega t minus theta, where theta was the arctangent of 2 zeta r over 1 minus r0, and H is the frequency response function, right? So now you have what? You have some of these functions, right? So now I can rewrite that f of t in this form. You have f a naught plus sum of n is equal to 1 to infinity of cosine terms plus sine terms. So u would be what? Response due to this is a constant, which is, of course, a static displacement, plus a n over k sum of n is equal to 0 to infinity of this cosine n omega t minus theta divided by or multiplied by the corresponding uh, frequency response function, 2 zeta n r squared, okay, plus b over n k, n goes from 1 to infinity times sine n omega t minus theta n, I would put this subscript here, times that. So that would be the response under periodic excitation. I'm sure you say that, wow, this is a nasty looking expression. So we'll see, we'll do a few problems to show you actually it's very easy to, you know, find the response under periodic excitation that you encounter quite a bit in mechanical systems. For instance, cam drives or sawtooth excitation is something like that. So I know that I'm not going to be able to solve that problem, but let me set it up and we'll do that next time, at least to show you an example. Okay. So let's say you have a damped system, okay, that looks like this. You have a system supported by this stiffness and damping element. And in fact, the values are given. Let's say this is zero point 0.2 kilo Newton second per meter. K, K2 is 3.5 kilo Newton per meter. And another stiffness element here, K1, which is also the same, 3.5 kilonewton per meter. Now, this is connected to a uh, drive that moves by the action of a cam. So you have a cam that is moving this up and down. This cam is rotating at the frequency of 60 RPM, which is what? 2 pi radians per second. Okay. So the mass of the system is given 20 kilogram, and the damping coefficient is given as 0.2, as I gave you that there, kilonewton second per meter. This cam drive represents a sawtooth function that looks like this. Okay, the maximum uh, peak or the lift, or we call it cam lift, okay, is 25 millimeter. So this is basically function represents the motion of this cam. Okay. What we want to find is this, and as I said, would be what is the maximum displacement that this system would experience. Okay. So here you see a good practical example. I'm going to stop here, of course. I'm not going to solve this problem. I'll do that next time. But this is a simple mechanical problem. You have a system that is driven by this cam, which is doing what? It is inducing an input displacement. So at least I can set up the first part, right? That equation of motion would look like this then, right? If you set up the equation of motion, which we'll do next time, you see it would look like this. And we want to solve this problem and find the maximum displacement. All right, I'm going to stop here. Any questions